This is the video key for our review for chapters 16 through 19. Again, these are the memory aids, formulas you'll be given on the exam. If you need anything else as you go through, make sure you memorize it. So our first problem talks about how they had a question about assault weapons. Should they be repelled, etc. The important things here is it tells us to ask a question to a simple random sample, SRS, a simple random sample, of 1,000 adults in Texas, and to a separate simple random sample of 1,000 adults in Indiana. So someone said, well, hey, instead of randomly surveying 2,000 adults, that's actually more work. We have to randomly select them. We have to go to their houses or call them or however you did it. It's quite a bit more work. It would be cheaper and easier to just announce the question on TV and ask people to call in with their opinions. Is this a good idea or a bad idea, or why? Now, before you look through at the answers, it's always best to write down your answer and then see what matches. So anytime you ask people to call in with their opinions, you're going to get a huge volunteer bias or volunteer response bias. So anytime people have to call in, you're going to get people that feel very strongly. Because if they don't feel strongly, they just don't care enough. So you're going to get a huge bias here. Okay, let's see. So let's look at their choices. This is a good way to get information about the opinions of all adults. Well, definitely not. We said it's a huge bias, so it's not a good way. Let's see. It's a bad idea because if only a few people call in, you'll have too much bias. That's not really our biggest concern either. Sample size, bigger samples are better, yes, but sample size isn't really our biggest concern. Our biggest concern is it a good sample? So I think I might make a note here that having a good sample is better than just a big sample. So we do like bigger samples, but our bigger concern here is that bias that we're going to have to deal with. Okay, let's see. This is a bad idea because allowing people to volunteer may result in a large bias. Well, that seems like what I had here, so I'm guessing C is probably right. Let's keep going. This is a bad idea because there's no control group. Well, we do like experiments with control groups, but again, that's not our biggest deal here. And this is a bad idea because the study isn't double-blind. Again, we like double-blind experiments. This isn't really an experiment, though. It is just an observational study. So those things don't really apply. Again, our biggest concern for this survey would be that voluntary response bias. Next, a gambler will play roulette 100 times, betting $1 on a four-number bet. That means if one of the four numbers comes up, she wins $8. If any other number comes up, she loses her $1. So this bet pays 8 to 1, and there are 4 chances in 38 of winning. So first, we're going to make a box model. Okay. So her total winnings in 100 plays is like the sum of how many draws from the box. Well, if she plays 100 times, it would be 100 draws from the box. When you make the box, there are 4 chances to win. So there would be 4 chances to win. So this is if we win. When she wins, let's see, she gets $8. And then over here, we'll put lose. If there are 4 out of 38 chances of winning, 4 minus 34, or 38 minus 4 would be 34, and when she loses $1. So make sure that's negative. So that's our box model. Again, 4 ways to win, $8. 34 ways to lose $1. How much do you expect her to win? Give or take bling. Okay. So when I look at this, how much do you expect her to win, give or take? That means we want to find the EV for the sum and SE for the sum. But we have a few steps first. We don't know the average of the box and we don't know the standard deviation of the box. So let's find those first. So the average of the box is going to equal to, well, I have 4 8s. So it'd be like 8 plus 8 plus 8 plus 8 4 times. So 4 times 8. Plus then I'm going to have 34 negative 1. So I need to add that up 34 times, or I could just do 34 times negative 1 if you don't want to put it in your calculator 34 times. And there are 38 total. So average, you always add everything up and divide by how many you have. Looks like we're 0.1053. And the standard deviation of your box, this is where we get to use that shortcut formula. And in fact, I think I'll come up here and do this. Anytime you only have two types of tickets in your box, you can use this shortcut formula, which makes things much easier. And the shortcut formula is big number minus small number. Now on the exam, I won't ask you to find the standard deviation of the box unless it has just two numbers like this. Otherwise, I'll just tell it to you to save time. Let's see, and now we're going to times it by the square root of the fraction of the big number times fraction of the small number. So in our case, our big number is 8 minus our small number, which is actually -1, so that is going to be minus a negative, times the square root, fraction of my big number. Well, we had 4 out of 38. And fraction for the small number, there are 34 out of 38. Sorry. Well, let's see. So here I get 2.76 for the standard deviation of the box. But I double checked while I had it off, and I wrote down the wrong average of the box. So the average of the box, sorry about this, is -0.0526. And then the standard deviation is 2.76. Now that you have the average of the box and standard deviation, it's really easy to find that expected value and standard error, because expected value for the sum is equal to your number of draws times the average of the box. So we have 100 draws times -0.0526, which gives me -$5.26. So I expect if she plays 100 times that she's actually going to lose about $5. And the standard error for the sum is equal to the square root of your number of draws times the standard deviation of the box. So square root of 100 times 2.76 gives me 27.6. That's actually quite a big standard error. And kind of out of room here to write this, but it is important. So we expect she will lose about $5.26. All right, let's go back here. We expect if she plays 100 times, she will lose about $5.26 total, give or take about $27.60. So that's a pretty big range. She might actually come away positive. It's like losing $5 plus 27. She might come out positive, but she might lose around $30 too. So let's look at what is the chance that she has made money at the end. So when it says, what's the chance that she's made money at the end? Let's see. Let's just make a note that was supposed to go up there. Okay, so the chance that she's made money at the end, that means we're looking for the probability that our sum is greater than 0. Well, anytime you're looking for the probability or chance for a sum, you know you're going to have to use the normal curve. And anytime you use the normal curve, you have to standardize. So let's look at how we standardize for a sum. We're going to z equals our sum minus our expected value for the sum over the standard error for the sum. Now the sum we're interested in is 0. The expected value is -5.26. So again, this is a negative minus a negative. Let's see, divided by 27.6. So 5.26 divided by 27.6. We get 0.19 as our z value. So if I was to draw this, z equals 0.19. I'm looking for, we want her to make money, so it has to be greater than 0. So we'll look for the area to the right. Now if I pull up my normal table, remember my normal table only gives me areas to the left. So we're going to have to do some work with that. So we wanted z equals 0.19. Looks like my closest value here would be this 0.20 at 57.93. So this area to the left is 57.93%. So if I want the area to the right, I'll subtract that from 100. So 100% minus 57.93% equals 42.07%. So there's about a 42% chance that she will come out actually making money. Now remember, on the exam, the person that writes it might use a slightly different table, or she might round differently. So if you get 42 and the closest answer is 40%, just go with the 40%. So we're just looking for that closest answer. Okay, so on this one, we looked at her total winnings. So total winnings is what we did in the last few parts. But now, what if instead of looking at her total winnings, all she wants to do is just count the number of times she wins? So anytime you want to count, you have to make your box model, but you'll have win and lose. Anytime you win, you'll put a 1 because that's what you want to count, and when you lose, you'll just put a 0 because that's not what you want to count. So whatever you want to count is what you put the 1 for. And you want her to win 4 times, or 4 chances to win, and 34 chances to lose. So it looks almost the same, but we switch when we're counting to, instead of our actual values, we switch to 1s and 0s so that we can count. So how many times should she expect to win, give or take? So once again, we're back to trying to find that average and standard deviation of the box. So I'm going to come up here to start to have a little more room. So the average of the box, I'm going to have to do 1 plus 1 plus 1 plus 1 4 times, or 4 times 1, plus 34 times 0, because I have to add on that 0 34 times, divided by a total of 38. And this one gives me 0.1053. And the standard deviation of the box, so this average of the box is supposed to be down here. Standard deviation of the box is equal to big number minus small number. So my big number is a 1, so 1 minus 0, times square root, fraction of the big, so we have 4 out of 38 that are big, and 34 out of 38 that are small. This should give me 0.3069. Now, expected value of the sum is equal to your number of draws times the average of the box. I like to write out formulas every single time I use them. It helps me memorize those formulas. Okay, so we're still drawing 100 times, and the average is 0.1053. So it looks like 10.53. So we'd expect her to win about 10 times. And standard error for the sum is equal to square root of your number of draws times the standard error of the box. So square root of 100 times 0.3069 gives me 3.069. So we would expect her, oh, that shouldn't be a dollar sign. It's how many times she wins, that's not a dollar. So we'd expect her to win about 10 times, somewhere between probably 10 and 11 times, give or take 3.069. Our next one says, the blank histogram for the sum of 100 draws approximates the normal curve because of what? So this goes to chapter 18 where we talked about, remember, our probability histograms, our theoretical probability histograms. So anytime you take the sum of something, eventually it's going to look like the normal curve if you draw enough times. Okay? So the probability histogram for that sum looks like the normal curve because the central limit theorem, which I don't think we talked much about that actual name, but the person who writes the exam just throw it in there sometimes. The central limit theorem says that if you have enough draws, the sum from any box, it doesn't have to look normal itself, the sum from any box will start to look like the normal curve. And at 100 draws, that's enough that any sum should look like the normal curve by the time you do it 100 times. And finally, suppose the gambler in the question above loses 10 times in a row. She decides to continue playing because she's due to win by the law of averages. But a bystander advises her to quit because her luck is cold. So who is right? Okay, so as you read through the choices, someone might say, well, games of chance are just based on luck, or because she's lost so many times, surely she's going to win the next time because of the law of averages. But neither of those are actually right, because each play is independent of the last as long as everything is set up fairly. And so even if she has lost 10 times in a row, and we do know statistically speaking that eventually she'll probably even out to a certain percent, each play is independent of the next one. And so knowing she lost 10 times doesn't tell me what will happen next. Next, a child plays a game of chance. Each game is independent and the chance of winning is 63%. In each case, which is more likely, or are they about the same? So first, I would set this up and draw, and I know, okay, we expect her to get 63%, and I know I'm going to kind of bounce up and down and eventually settle around 63%. Let's see, so we want to win more than 65% of the time. So if you want to win more than 65% of the time, when is that going to happen? More than 65, that'd be up here. So to get more than 65, that's probably going to happen in the beginning. So that would be more likely to happen at 100 times. So let's go with 100 games. Okay, winning between 60 and 65% of the time. Well, again, here's 63%, and I think I'll kind of bounce up and down and eventually even out about 63%. So if I want to be between 60 and 65, here's my 65. Here's my 60. And when am I going to be more guaranteed to be in there? If I come out to a large number, I'm going to be more guaranteed to be in between those two values. So if that was 100 and this is 1,000, I'll be more likely to have it happen in 1,000. Our next example, at a made-up university, there are 40% of all the students that are older than 25. Notice that all, anytime in this class you see all, that's going to mean your population. We take a sample of 30 students and look at their ages, and we find that 34% of the students in our sample are older than 25. And when you start looking at these questions, it's talking about what's the population, what's the sample size, sample statistics, parameter, etc. So what is the population? Notice we only sampled people at this specific university, so we can only look at this specific university. So I would say it would be all students at this specific university. Now, what is the sample? That would be the 30 students at this university we studied or surveyed. What is the sample size? It looks like we took a sample of 30 students. What is the sample statistic? The sample statistic is whatever numerical value you took from your sample. So it looks like we looked at the 34% of, so it's the 34% is our statistic, or it's the percentage in our sample. And what is the population parameter? That would be what number did you look at in the population. So that would be the 40%, or basically the percentage in our population. So sample statistics are always, or statistics are always for your sample. Parameters are always for your population. On the exam, it will not say sample statistic, it will just say statistic. Okay. Next, we have another survey. Let's see, it says once each year, 1,500 adults are interviewed in their homes all across the country. The subjects are asked their opinions about marriage, etc., etc. Okay, so first, the population for this survey. Well, if we look at the population, let's go see who they interviewed. It looks like we had adults that are interviewed all across the country. So our population should be all adults in the US. So I would go here with I. The study finds 28% of the 1,500 people interviewed do not approve of capital punishment. The number 28% is a statistic because it was the percentage in the sample. Okay, now it tells us how they do it. So they begin by selecting a random sample of counties from a bunch of counties. Then they take each of these counties and they divide them into townships and then take a random sample of those. And then for each of those, they randomly choose households. So it looks like they started kind of doing a cluster. They took a couple counties, those were clusters. But then they kept going. So they took those clusters and divided them into more clusters and divided them into more clusters. And each time they just kept going through the cluster. So that would be a multi-stage. So a potential source of bias in the study would be some subjects refuse to give their opinions. Well, that would be the non-response when people refuse. The sample design chooses dwelling units, so homeless people are left out. Well, anytime you leave out groups of people, that's selection bias. And let's see, last, interviewers may unwittingly affect the responses from the adults. So anytime your interviewers kind of affect things, we call that response bias. On the exam, you're most likely to be asked about non-response or selection bias. But in this case, all of those would be potential sources of bias. And last question. Here's the histogram of the box. It has 2 zeros and 8 ones. So if you look at the histogram, notice like it would be kind of 2 zeros, 8 ones. This is one that we'd kind of call like a long right tail. Notice it is definitely not symmetric. Sorry, not long right tail, long left tail, because it goes off to the left. Let's see, below are some probability histograms for the sum of the draws from the box. So match each image to the number of the draws. So when you look at this, all you really have to remember is that the more draws you have, the more the probability histogram of the sums look like the normal curve. So if we have 3 choices here, 5, 40, and 400, the one that looks the most like the normal curve has to be the biggest, so that would be 400. This one's kind of in the middle, so 40, and this one would be 5. So notice that 5 is still very left skewed. It has that long left tail. At 40, it has a kind of long left tail, but it looks pretty close to the normal curve. It's getting there. And at 400, it looks perfect, just like the normal curve.